Hi, welcome back. I hope you caught that cool musical experience over on the fun track. That was great. I was doing some dancing, like under the desk dancing over here. And so now we're all ready for our next talk by Alex Ellis. Alex, some of you might know him. He's a respected expert on serverless and the cloud native computing foundation ambassador. Um, I'm personally very excited to see you because I don't know if you know, but I'm organizing Serverless Days Amsterdam with my good friend Mark Dowker. And so after this, I'm going to ask you if you want to speak at our conference meetup maybe someday. But in the meantime, let me just tell you a bit about Alex. So he founded OpenFast, which is one of the most popular open source serverless projects. And he's a community builder. He writes, he speaks, he engages personally with you. He will come to your birthday party and generally just helps companies around the world build great developer experiences and navigate the exciting world of cloud native. So, Alex, are you ready to go?
Yeah, I'm all set. And there's not going to be too much about serverless in today's talk, but Amsterdam sounds good.
Awesome, cool. All right, then, Alex, take it away.
Okay, so I'm going to share my screen and we'll start this presentation I put together for you. And the talk today is on introducing cloud native through the vision of bare metal and how can you kind of make the two make sense together. Once we've had a look at those, we'll then look at the tools and technologies. You'll find that some of them haven't changed for 20 to 30 years, and you might actually remember some of this stuff from way back in the day. But because it hasn't changed, we need to sort of think about, well, how can we automate it better? And there's a number of different software projects that have come about to help us with that. And we'll look at, well, what is the workflow? What are the opportunities? And then some of the projects that are tackling it. We'll also think about how can we relate that back to running on Kubernetes, and there'll be opportunity to take it further at the end. So when I think about bare metal, this is one of the first things that comes into my mind is just having a look at this image here. We've got a cabinet. You're probably not allowed to be in this room for, high security. It looks like it's in a warehouse or a garage. Everything looks the same, peace and calm, very well organized. I don't know what you think when you think of bare metal. Maybe you think of this, if you've actually had a bit of experience with servers and infrastructure. And when we zoom in, we see there's actually a bit more going on here. We've got storage arrays, we've got compute, lots of networking cables. And if something went wrong there, you could potentially spend a very long time tracking it down. The kind of thing you probably don't come into when you're playing around with Kubernetes or Minikube. Now, I actually got a chance to get up, close and personal with a server. Ampere Systems sent me this Lenovo, and it's got one of their CPUs in it. And you can see, compared to me for scale, how big this was. It was actually pretty heavy, quite hard to carry on your own. And it's very, very big. Sort of show you the scale of it. That's what it looks like on my couch. And you see at the front, we've got things like hot swap bays, things that you probably wouldn't have on a normal PC. And then I set it up, and you can see it's taken up an entire dining room table for 4 people, just to put a server down. And think about your MacBook, sort of squeezed in on a coffee shop. This is way, way bigger. And also with that 256 gigs of RAM, you never get that in a MacBook Air. It also makes about 200 decibels of noise. I mean, you wouldn't want to be sat next to this all day. They're very, very loud. But this is what servers are like. And it was my first real experience of handling one. And it wasn't quite as expected. And there's a few things that really make a server a server. I'm not talking about a TCP socket here, about a real machine, purpose built. So we tend to have a couple of network interfaces on these, and it's not your gigabit that you're used to on your Raspberry Pi, probably 10, 25 gigabits, maybe some redundancy there. going to have an out of band console to access those computers and reboot them and do operations on them without having to get inside those big cages or the glass enclosure that you see here. Do it all effectively hands-free over the network. When it comes to storage, again, everything is redundant. You've got maybe 2 network ports. You have 1 or more RAID controllers in there, and the drives are probably hot swap, where if one fails, you can literally just swap it out with the machine powered on. You're not going to be able to do that with your home PC. And in terms of booting, again, more redundancy. You've got 2 power cables going into that, drawing full power down. And whilst the server that I had there, you can boot it off 1, it's recommended to boot it with 2. And you'll be surprised. You turn these on and it will literally take 5 to 10 minutes to check itself. Again, I don't think people would tolerate that on a home PC. And they do tend to have a better firmware on them. So my Intel NUC here, it doesn't come with the latest kind of network booting firmware called iPXE. It comes with just regular PXE. So I have to put a USB drive in there, try and flash its ROM. It's a pain in the neck. Servers are not a pain. They have everything that you need, and people have thought about this already. Now, you might also be thinking, well, great, well, that doesn't really apply to me, but I think even Raspberry Pis can be considered bare metal, because we're looking at working with real hardware and not with virtualized machines or cloud. And so you can even go, this company Bitscope has this rack mountable unit, and we can put sort of 30 of these Raspberry Pis in there. They've all got 4 CPUs, and you can imagine what kind of stuff you could do with that. But you've got to be careful, because ARM processors don't run normal Intel code. Most code's compiled for that. And so you have to maybe rebuild it, maybe have to search out specific packages. Tools like Istio just plain aren't supported right now, because it's too much work for the projects to add support. So bare metal is really, it's not all the same size and shape. The CPU can differ. You might be working with an Intel CPU or an AMD one, and they may have different instruction sets, different optimizations. You may be having that ARM server from Ampere I showed you, or an IBM Power Z14 in the corner of your office, which is like an entire cluster all built into one big box. And the way we talk about this is as heterogeneous. So whether that is IoT in a big rack or small home and office, going back to our Intel NUCs or your HP microPoliant, everything is probably going to have varying standards of interface, varying firmware. That Intel NUC doesn't have 2 network cards, for instance. So maybe you have to add things to it. That's servers and the different types of servers that we can get. If you don't want to go and purchase your own kit, I wouldn't advise that you do if you're just playing around at home. You can go online and in the bare metal repo, I've added in these cloud providers. Each of them will give you a full machine. It's completely yours, but the great thing is you can manage it through an API.
So it's already starting to feel a bit cloud native. Someone else's infrastructure, but it's bare metal. Now, my wife asked me, she said, well, why have we got this tower in the corner of the room? And I said, well, look, it's a bit like this. Think about apartments and a detached home. An apartment is cheaper to get up front. It's fully furnished, most likely. All your utilities are paid most of the time. That's the arrangement. But you can run into this problem of your neighbors can get really noisy, or maybe have a party all night and you won't get any work done, right? Or at least not as much as you wanted to. Contrast that with a detached home, the bare metal server, and you have, as much space as you want, complete freedom to run the show how you like, but it's your responsibility for upkeep and for the bills. Also, they might be prone to waste. Think about that 5th bedroom. Do you ever actually use it? Have you got 3 bathrooms? Do you use all of them or all of your garden area, right? And so we have some pros and cons here. This is like a nice analogy if you're not too familiar with this area. When it comes to use cases, it might just be that you already have some of these servers. Some of the clients that I've worked with recently had their own data centers, legacy data centers, so you might as well use it. And there may be services running there that you can't migrate. There's just not suitable hardware in the cloud to take it over to. Data sovereignty is where you need to have deep control and access over all of your data, maybe doing payment processing. Some companies need to do that on premise. Dropbox, for the total cost of ownership, brought their AWS workloads back on premises. And they did that because it was cheaper. Cloud's meant to be, so great. A lot of management is done for you. We saw those servers, how complicated they are. But Dropbox were actually like, well, the cost in the long run is cheaper for us. And you won't hear a lot of people sort of talking about cloud in that way. The other thing is when you have your servers in the cloud and you want data to come out, people don't usually think about the cost of that bandwidth, but you are charged for it. And some people have a commentary on the cost of this on Amazon, AWS. It is actually pretty high. So if you're doing lots of data transfer, you're probably going to be cheaper running your own server. Now, something that Packet are particularly good at is this last mile latency. So you can boot up a server in Japan, you can put one in your warehouse somewhere, have it managed by an API, and then whoever connects to that last mile between their house perhaps and the code, maybe it's an automated car or electronic car, that can be just as fast as it can get. Maybe it's cached at the edge. And then the last thing is that you might just want a very predictable performance, right? Where like that house analogy, that this is your capacity, this is your IOPS, and you guaranteed it. Okay. That's bare metal use cases. And when we look at where does that really fit? Well, I find this quite useful as a way of thinking about it. Monolithic software is very big and complex as one big block, right? And that corresponds roughly to maybe a bare metal server, lots to do. As you move over to the right, you have these microservices that run better on VMs, on premise or in the cloud. And they're broken down into smaller bits. So there's less for you to have to worry about. Certainly at the microservice level, you're not worrying about whether you can network boot. And then you get over to the functions right on the other side, and there we're really looking at the most granular approach we can get. Can we transform this JSON payload into a different payload and maybe alert somebody about it? You really don't have to think about servers at all. So when we look at it within this context and on these two axes, this is probably where Amazon would be, like Lambda on the far right. So we just write a bit of code, and I've literally just been billed only for 100 milliseconds. And it turns out those 100 milliseconds were within my free tier that AWS give you for free. So compare that to owning a server, configuring it and running it on premise. I think it's pretty clear this is much better. But it does come with some drawbacks. Whilst there's that low overhead up front and that initial cost is practically zero, there's very limited customization. It's not well suited for certain use cases. You can't run a database on Amazon Lambda, for instance. Really, it's great for responding to events. It's great for doing stuff like maybe serving a web request. But there's a limited performance. At some point, you can't pay them more to get a faster computer. There's a cap on it. The code is also, whilst it might be written in something like Node.js, it isn't particularly portable to take that and run it on Kubernetes, right? Because suddenly all of that stuff Lambda was providing you for isn't there, and the cost does increase. So if you find you're utilizing that function as much as you would a regular server, it might actually be cheaper to run that on EC2 or on your own VM. Okay. Serverless 2.0 is where Kubernetes comes in. And this idea is that we can decide the limits on our own. So if we can run it in a Docker container, then it's fair game for Kubernetes and serverless 2.0. You can run that at any scale simply by, let's say if you're using Amazon, having an auto-scaling group and add more nodes in. So it's nothing against AWS. Lambda is a great product, just it has limitations and they may not suit your business. You can also then take that on-premise servers and public cloud servers, and you can kind of bridge them together in hybrid cloud. You could run this across multiple clouds, and that's kind of where this all fits in. So for bare metal, you do everything yourself. AWS Lambda, very low cost initially, but very limited. And then serverless 2.0 is sort of where you start to bridge the gap. And we'll go back to networking. These are some of the technologies that haven't changed in sort of 30 years. You might have heard of Pixie. This is traditionally what you'll find on something like an Intel NUC out of the box or on my Raspberry Pi down here. And this is a way of telling the computer, you don't need any storage to start up. It will actually look to the network and it uses DHCP and asks for an IP address. A server could then say, here's your IP, but also go to this address on TFTP, download a firmware, and then it can start running it. Okay, and that's basically how this chain works. We'll see a diagram in a second. The other thing is that you might want to mount some storage over the network. So whilst we may have an empty computer, no storage, we may want to run our actual file system over the network. Right? Makes it very reliable. This just becomes a processing machine. The other way of network booting is that you'll set up over the network, but then deploy on the local hard drive afterwards. So diagram, I always like a diagram. We start at the top. Our unprovisioned server said, I want an IP address to the network, and it broadcasts that. So it doesn't know particularly who's going to answer it. Then a DHCP server will say, okay, here's an IP, and go to this TFTP server, trivial FTP, download your boot bin. It will then go, okay, TFTP server, can I have that, please? It will then give it the file. It will run that. And if it's Linux, for instance, it maybe will contain a kernel that will get booted up. The kernel will run what's called an init file system or init-rd, number of steps to turn on different drivers. And then at the end, it's either going to mount a network file system or it's going to go and say, right, well, what do you want me to do? And it might give it a bunch of scripts to format its own hard drive. Okay. So I've actually got a demo of that for you. And we're going to do it on a Raspberry Pi because this is bare metal that anybody can get. And you can set this up, or only take you a couple of hours really to configure your server. Now the way that it's going to work is I've used DNS mask to configure these two services we talked about. NFS for the actual boot. And whilst normal computers, what they'll do is they'll broadcast and say, can I have a firmware for my MAC address, unique MAC address? Raspberry Pi asks for the serial number for some reason. So what we have is we have a bunch of files in an NFS folder. And these are all, you see, serial numbers. And if we look in the TFTP side of that, we've got a bunch more in there as well. What we'll do, I'm going to reach down and grab the cable. These are the logs of the DHCP server. And I'll put the cable in. You can time it if you're interested. So 17:14. That's now powering up. And if all goes to plan, we've got the lights on the back. Very shortly, we just got it. So within 14 seconds, it asked for an IP address. It was given one. And you can see what I mean about this is the serial number, right? And so it's now booting that over the network. We'll see what IP it got was 114. Let's go and see if it's up yet. You can use SSH to get into it.
Sorry, Alex, could you increase the size of the font a bit?
Sure. So that's about as big as I can make this. This is where the TFTP server served the file. This is where the IP address was asked for. And this is the basic workflow that any tool that you use is going to use something very, very similar to this. Okay. And now I'm in the computer. If I look at what's mounted, we'll see a whole bunch of stuff. But if I look at the disks, see there's just one, and that is a USB drive that I've plugged in so we can run some containers on it. But basically, the root file system is coming over the network, and that's that. So all you need to do is effectively create those 2 directories, plug in the Raspberry Pi. If you've got another one, create 2 more directories, plug in the Raspberry Pi, and that's it. What you then get to is, we'll see how big we can make this, is you get to the point where you can actually do a Kubernetes cluster. And this is one that I made earlier. It's got 4 in it. And we can see all their IP addresses on here. And I've done a port forward for OpenFAS. And we'll see, this is the OpenFAS UI. It's running an ARM. Remember, we have to compile it for ARM. We go hi matters. Actually, this message isn't going to get printed out anyway, but this is a node info function. It's going to tell us about the CPU. It's exactly the same as we did on Lambda, but it's running on Kubernetes that's net booted. And I've got my 4 computers. I can add more if I want. And that's a demo of net booting. So in about 20 seconds, I've got from 0 to booted system. We also have Kubernetes installed on another one. And it's reasonably easy to do. Okay, but it's not automated. And that's really what the next part of the talk is about. So the services that we saw, we want an IP address from DHCP. We want to be able to serve the data over TFTP. Then we want something like NFS or HTTP to give us the actual files to load up, okay, or the workflow. They have to be automated in some way. It needs to be a bit easier. Then have this inventory and discovery. So the Raspberry Pi will broadcast its serial number over the network, but normal computers broadcast their DHCP, their MAC address, rather. And you can then use that to form a catalog, so we could discover them. There's a project called Plunder, which discovers IPs and puts them in a catalog. There's projects like Tinkerbell, where you should insert a JSON file for every machine you want to onboard. And then you've got to decide, well, how am I going to build an image that I can run on this? You can't necessarily just take a USB drive and plug it in anymore, or a CD, because this is all done over the network. So again, we have a whole area of image building just dedicated to that and management of those images. Delivery and provisioning is where you'll then take that computer that's booted up and you'll put the image on it. Okay, and these are all of the kind of things where we can get help from software. Now, there's a GitHub repository I put together called Awesome Bare Metal, and this was really sourced from the community, and it's a curated repo. Some of the most famous sort of projects at the moment are things like Digital Rebar from RackN, Ironic from the OpenStack Foundation. OpenStack's got a really rich pedigree of this kind of thing. Canonical built out a service called Metal as a service. And most recently, we have Tinkerbell from Packet, which is really focused on automating all of this as well. Now, you don't have to have a full automation. You could use something like NetBoot XYZ. I actually used that yesterday, and I put it into my PC. It allowed me to install Ubuntu, CentOS, whatever I wanted over the internet without actually having to flash a USB drive. So there's multiple purposes for this. Now, the Tinkerbell project from Packet, that has broken this down, I think, quite nicely into 4 different services. There's one called Tink, which is where you would actually define, okay, format the disk, then install Grub, then install the root file system, and then maybe, I don't know, run cloud in it. If you want an example of how that all works, you'll find it in my repo at the end of the talk. BootS is your DHCP and your Pixie server in one thing. So on my demo, I showed you DNS Mask. It's a standard Linux tool. Well, what the team here have done is rewritten everything in Go. So it's all managed in a couple of binaries. And then OC is one of the bits I'm most interested in. Effectively, that's a software that runs over the network, but actually it will run on your computer. And then once it's loaded up, it uses Docker images to go through each automation step and set your computer up. And then we have Heagle, which is containing all of the different metadata. So if you boot a computer, you can use Heagle then to define exactly, well, what kind of computer is it? What's the username? What's the security story? So if you're interested in trying Tinkerbell, there's a lab on packet.com. It was set up with Terraform to give you 2 servers. You then run something to install Tinkerbell. And I actually used this at home yesterday. So, you know, if you've got PCs at home, you can do that too. And everything's running in a Docker Compose file, just the one. So it's all in one place. There's a nice CLI for it. Everything's done in JSON. So if you've seen enough YAML, you'll be happy to see this. And then the workflow steps are basically Docker images. So formatting the disk is a Docker image, which means that you can version that, you can put it in a registry. I actually quite like that workflow. And then that OZ environment is built with Alpine Linux, so super fast. This is one that I did earlier. So if you want to try it out, there's a lab at the bottom. It took me a couple of days to put this together, but it is working. So what you can do is build an image out for Ubuntu. They've got ARM64 support as well. And then what this will do is it will run that OZ on the computer after net booting it, format the drive, install your image, and then the next time you boot up, you basically just got a working machine. Now, that is automating all of that sort of older technology, right? But at some point, we want to make this a bit more cloud native, and the first project in the CNCF was actually Kubernetes. Well, once you've got your PCs with your OS on, you can use something like Ketchup, which is a SSH installer for K3S, Ansible, CubeSpray, which is kind of a mix of the two, or even just Bash, right, to install Kubernetes and form a cluster. But there are a number of projects that you might find interesting too. I've listed them here. One of the ones here, Locomotive, is by Cobalt, that have sort of taken the reins over from Core OS. I think they were all very interesting, and the fact that there's so many, I think, means this is an area that needs more investment. And some of them will get you to Kubernetes, but some use this thing called Cluster API as well. Cluster API, we'll have a look at in a second, is a declarative way of putting the clusters together. Right. Now, one of the tools that's going to be the easiest for you to try is Ketchup. It's a community project. And if you ever installed Docker Swarm and you liked that experience of init and join, you kind of get that back for Kubernetes. So here we can install a cluster across an EC2 VM running K3S up install, and then join against any number of nodes. Now, this uses SSH, and that's it. At the end of it, you'll get a kubeconfig. It's super, super fast. I actually used it on my Raspberry Pis. And K3S will give you production-ready Kubernetes. It is good for the edge, but that's not the only place you can use it. You can actually use it wherever you want, and you can pay Rancher for commercial support if you need to. Now, the Cluster API project uses kubeadm, so the more traditional upstream Kubernetes. And what happens here is effectively you start off with a seed cluster, might be on your laptop, might be somewhere else in your network, and you just define in YAML what are the hosts I want, how are they meant to look, and it will go off and build the cluster for you. Right. But there's still a little bit missing in the story. So we've only really covered compute, and whether you install a Ketchup cluster or kubeadm or Cluster API or COPS, at the end, you're missing certain parts around networking and storage. And we haven't really got time to talk about that here, but in the awesome bare metal repo, you'll see some links to different projects like MetalLB and Inlets that can help you bring some of that functionality back again, like you'd have in the cloud. So to sum up, there's a lot of information there. We've gone on a journey from bare metal and servers, what makes a server. We've gone through to how does that differ to something like Lambda, where does that fit in the cloud native landscape, to actually what are the tools. Okay, so the workflow is we use DHCP to get an IP, and then iPXE or PXE to boot. we're probably going to pull some files over HTTP or NFS, install something, or just boot over the network. Then we're done. From there, it's on for you to think about your post-provisioning steps, like, do you want to add some storage? Do you want to run Kubernetes or something else? And then we've also had a look at automation tools, right? What's my inventory? It's probably all very different. So how do I create an API around it to look at it in a cloud native way? How do I define what I want to actually do on the machine? And then where do I get my OS from? That's really what we covered here. There will be a recording of this, so if you want to go through it again at a bit of a slower pace, you can. And the last thing I'll leave you with is, if you want to sort of connect with this and learn a bit more, there's the awesome bare metal repo. It's got all the projects we talked about listed there. The Packet Slack, if you want to try Tinkerbell or just bare metal in general. And then the OpenFAS Slack, if you want to kind of get in touch with me or you've got some questions about serverless. Okay, so that concludes the talk. Thank you very much.
Thanks, Alex. That was great. So I'm just checking if there are any questions. I think this is more of a comment, but Thomas says, nice, we'll definitely check Tinkerbell. Have been experimenting with mass in the past, but couldn't get RPIs enrolled in it. Do you have any
RPIs
for Thomas?
I'm not sure what an RPI is, but do drop into the Slack for Tinkerbell or OpenFAS, and happy to have a chat with you about it.
Okay, cool. He also says that this project may also fit in this list, and then he linked to the Weave Kubernetes system control. Is that in the list?
So the list is completely open source. You can have a look at the guidelines for submitting a project, and if you think it fits, feel free to send a pull request.
Awesome. Cool. Did you hear that, Thomas? You can be a contributor if you want to. Oh, Marek Koshinsky from AWS. Hi, Marek. Is asking, and I'm not sure what the question is actually aiming at, but his question is just Raspberry Pi smiley face.
Yeah. So a lot of people have this kind of thought. There's two schools of thought on this. One is Raspberry Pi is a great tool for learning, being able to demonstrate something as complex as booting a bare metal machine in Kubernetes on a Raspberry Pi that costs $30. Other people can be quite derogatory or even, sort of confused at why you'd use a small device like that. I think one of the things that network booting brings is really reliable storage. Suddenly, you're not relying on an SD card and you've got four 1.4 gigahertz CPUs to do whatever you want. Companies like Bitscope are doing some really good production work, building out really large clusters of hundreds and hundreds of nodes where you just wouldn't be able to do that with PCs. You just wouldn't be able to afford it. So I think there's definitely some really interesting use cases for that. And I wrote a blog post up called 5 Years of Raspberry Pi Clusters. You can go find that on Google. It was on the Raspberry Pi blog, and there's some real use cases there as well you might find interesting.
Cool. Actually, Marek just wanted to suggest that RPI probably means Raspberry Pi, which in fact, that's what he meant.
Oh, yeah. No, Raspberry Pi. Yeah, of course, that's what he means. There is somebody from Container Solutions that's been able to use Tinkerbell with Raspberry Pi. I'm not using Tinkerbell with this. It's just very simply no special automation, just NFS, DHCP, both on DNS mask. And if you want that recipe, contact me on Twitter or send me an email. Happy to share it.
Awesome. Thank you so much for the talk. It was really great. And hope you're going to be kind of on the Umbrella event thing in case more questions are coming up. People are, they want to chat. There's one more question coming in. Do we still have time for a question? I think we might. Okay, I'm just going to fire this real quick. We see network booting in various places, typically places like train stations, airports, the departure boards, etc. They often are left at the PXE booting screen. What are other good use cases you can think of?
So why would you want to net boot a train or a display? Well, probably for the same reason that you don't want to go into that locked glass cabinet and start fiddling around inside of it, because it's just too hard. So yeah, I think if you can network boot the display in all the displays in an airport, you save yourself a lot of hassle. And part of cloud native and serverless is that idea that you're touching infrastructure less and less and less. You can provision it, plug it in, maybe provision itself when you plug it in. I mean, that would be great. Net booting, as I'm looking at it, is how can we make the data center easier to use? How can we apply cloud native, like API driven ideas to computers that are actually quite different, and make that easier?
Nice. Yeah, I mean, a conference, right? If you have like screens at a conference, which I'm seeing quite a lot, that could be a use case.
Yeah,
So
definitely.
yeah, cool. So I think we're quite slightly over time, but it's fine because we're heading into the lunch break on this track anyway. In the meantime, I think it's already started. You can go over to the fun track. There's a recap of the Counter-Strike Go tournament, and there's some funny bloopers apparently and stuff like that. So just grab like your lunch and then sit in front of the screen like every day for the past 3 months. Yeah, and join us for a blooper reel. And thanks so much, Alex, for joining us today.
Yeah, thanks for having me.
Yeah, of course, you're welcome. So we'll see each other at 1:15, so about 15 minutes from now.